Let's practice with these log properties. We're going to use the properties of logs first to expand a single log into multiple logs. And where we can, we'll evaluate those expressions without using a calculator. This just means that we don't want to use the calculator to get a decimal answer. We can use a calculator to get whole number answers or integer answers. So it's okay to use a calculator, but we want to simplify, not solve. We want exact answers, not approximate answers. I'll show you a difference with the first one. So the first one, log base 5 of 7 times 3. Property of log says if I'm multiplying inside, that means I can add outside. This is an exact answer. Log base 5 of 7 plus log base 5 of 3. If I wanted an approximate answer, I could do something on my calculator, but I've got log base 5. My calculator doesn't have log base 5. I only have log base 10 and log base e. I could use a change of base formula. Oh, that's too complicated. We're going to leave it like this. There's not an exponent of 5 that gives me 7. That's not an integer answer. And there's not an exponent of 5 that gives me 3. That's not an integer answer. They're all decimal, irrational numbers. So we're going to leave that as it is. In number 2, we still have multiplication, 1000 times x, so that multiplication turns into addition. This log does not have a base. Well, if it doesn't have a base, this is our common log base 10. This is our common log base 10, and so this first expression is asking 10 to what exponent gives me 1000? Well, 10 to exponents, 10 to the first is 10. 10 squared is 100, has 2 zeros after the 1. Any whole number exponent of 10 will be a 1 followed by that many zeros. So I have 3 zeros in 1000. 10 to the third power is 1000. I can use my calculator to check that. 10 to the third power gives me 1000. So even though instructions say without a calculator, we can use our calculator to check our answers. And since this is a whole number answer, we're going to replace log of 1000 with 3. And then log x, I don't know what x is, so I can't do anything to it. Log of 1000x is 3 plus log x. Looking at the next one, log base 4 of 64 divided by y. Division says we subtract on the outside. So log base 4 of 64 minus, repeat the log base 4 of y. And then we can play the same game we did before. 4 to what power gives me 64? Well, 4 to the third power gives me 64. We'll do a quick check. 4 to the third power is 64. So this is 3 minus log base 4 of y. And that'll be our answer for number 3. We're only expanding. We're pulling the log apart based on what's inside, so that we only have one thing in the argument of the log, one item, either one number or one variable. No exponents, no multiplying, no dividing, nothing in there except one item. Looking at number 4, log base b of x to the third. This is demonstrating the use of our power rule for logs. The exponent here can multiply by the log. And I don't know what base log I'm in, plus I have x for a variable. That's as far as I can go. Practicing a little bit more. Here I have log base e of the 5th root of x. Well, this log base e, this is really natural log. But for whatever reason, it's written this way. Just be able to recognize that natural log is really log base e. I'm going to make that change right now. We're going to call this natural log. And then the 5th root of x, I can write that as x to the 1/5 power. Any radical I can rewrite as an exponential function with rational exponents. So I want to do that because if I have an exponent, just like in the last problem, I can bring that exponent down front and then just keep the base in with the log. So log base e of the 5th root of x is equivalent to 1/5 natural log x. Combining our rules now, we have log base b of x squared times y. Notice that the square is only on the x, so I don't want to use that power rule yet. I need to first break apart that multiplication. That's the big operation that's going on with everything inside the log. So I'm going to use that multiplication to sum property, log base b x squared, log base b y with a plus. Now This 2 is only on the x, so the 2 will only be in front of the log with x in it. 2 log base b x plus log base b y. X is only one thing, y is only one thing. That's as simple as I can get. That'll be my answer. I'll let you try numbers 7 and 8 on your own. You can always go back and check the OneNote and see if you got it right. And we'll do just one more. I'm going to take a look at number 9 for that division. So now we've got all three properties. I've got a multiplication in the numerator, I've got a division on the whole thing, and I've got a couple of exponents in there. Let's look at how we can apply the properties of logs so that we can break this apart. And notice we'll end up with log base b of x, log base b of y, and log base b of z, adding, subtracting, and some exponents in there. The big operation going on inside that parentheses, big operation is division. So we'll start out with a division. X squared y, division turns into subtraction, and so we'll have the numerator and the denominator in their own logs with a subtraction between them. And now I can simplify the first log base b x squared y. I've got multiplication here, so that'll turn into x squared log base b y. I'm going to copy the next one over, log base b z squared. And then the last step is to pull those exponents down. 2 on the x will come down front. Y has nothing, so it'll stay the same. 2 on the z will come down. 2 log base bx plus log base by minus 2 log bz. And then one more. Oh, here's another one with that log base e. Just change it to a natural log. They mean the same thing. We can write this as natural log e times x to the 1/2. Both of them are underneath the square root, so both of them will get the exponent. Now we can do this in several different ways. We can either put the 1/2 on the e and on the x, because if you remember, if I'm multiplying inside the radical, I can break the radical apart. We could do that, but I'm going to use the log property first to demonstrate that we need to make sure that both the term with e and the term with x get that 1/2. Just showing you a different way to do it. So again, multiple strategies. I'm going to use the exponent property that says I can bring that 1/2 down, 1/2 natural log e times x. Notice that 1/2 goes to this whole log, e times x. So when I separate log of e times x, natural log e plus natural log x, the 1/2 goes to the whole thing because it went to the whole thing before. So just demonstrating that part. And then natural log e, I'm going to keep the 1/2 out here. Natural log e, this is log base e of e, that's 1. 1 plus natural log x. And then the only other thing I can think to do is multiply through by that 1/2, distribute the 1/2. We get 1/2 plus 1/2 natural log x. If we do it the other way, natural log e times x to the 1/2, we can pull that 1/2 in on each of those, and then we can separate with addition, log e 1/2 plus log x to the 1/2, and then we can see pulling the 1/2 down, get the right base of my log in here, 1/2 log x, and then natural log e is just 1, and we end up with exactly the same answer as we should, even doing it a slightly different way. So this demonstrates practicing expanding logs, pulling the logs apart, and getting simpler log expressions, but more of them. In our next lesson, we'll be putting the logs back together. So we'll start with something maybe not as simple as what's on the bottom here. We'll start with something that looks like our answer, and we have to go backwards to bring everything back together into one big log. The purpose of that, ultimately, for our class will be to take expanded log expressions and put them together into one log so that we can solve logarithmic equations. So that's the ultimate goal, but we need some practice using these properties to pull them apart and put them back together again for those very strategies. So come back for the next lesson to learn how we can use those log properties in reverse.